Design considerations. So what I've found over the years is that when people attempt different projects, they often do an overkill sometimes by selecting materials that are really too strong maybe for the application, or maybe, and then obviously the stronger it is, the more heavier it could be. Or otherwise they might choose a material that is too weak, and therefore the whole project is made, it fails, and then a lot of time has to be spent again to do it. So what we're going to be looking at is some design considerations of how different types of materials, maybe different shapes that are useful, different ways you can actually manufacture things. And in this way, you'll be able to use it in your different mechatronic applications. Okay, so over here I'm going to be talking about the material selection and properties, and we'll be looking at copper, brass, aluminium, stainless steel, and mild steel, and look at a few examples of how they are being used. So initially, let's have a look at copper. So we've had a look at some copper tubing before. So this is something that is quite common. It's used for water pipes, for example. And copper has got the advantage that it is conductive very easily. So as we did with thermal expansion, the expansion was very easily to be seen with the copper that was being used, with those copper strips. It is softer. So to give an example, I've got a copper rod over here, and I am able to bend it quite easily. So you'll see that it is bent a little bit over there. It is relatively easy to bend. Okay, so it is therefore soft. And what's nice about copper is that you can solder it. This is quite useful because sometimes you need to solder a wire together, and if they were not copper, you wouldn't be able to do that. So copper gives you that flexibility that you can solder, make good electrical connections as well. So copper is also good, not only a conductor of heat, but also a good conductor of electricity. And this is why most of your wires are made from copper. Copper does corrode, and so it doesn't rust in a sense of how iron might rust. But if you look at this copper pipe I've got over here, I've cleaned it up, especially on this specific side. Ignore this ring over here, we'll be looking at that soon. But as you turn this around, you would see it starts getting like a darker color, and most of the time it can, depending on especially if the temperature increases and decreases, it can change to a darker color. But if you look inside of this pipe, you might see a greenish color. As a matter of fact, I've got another pipe over here that has got some corrosion on it, and you'll see it's almost like a bluish color that it shows, and that is corrosion of the copper. And most of the time, if you look at your copper sulfate crystals, which is also a bluish color, so that is sort of the type of appearance that you would then see on these copper materials when they're corroding. Okay, then we're going to be looking at brass, and this ring on this copper pipe is brass, and as you can see, it's more of a yellowish color. So brass is a alloy, and it's a composition of copper and zinc. It is much stronger than copper, so it's much more harder. It's also conductive for heat as well as for electricity. You can also solder on brass, and there's minimal corrosion. So if you look at this ring, I've cleaned it up over there, and as I turn it where you would see the copper to be corroded, or at least also changing a bit of color, you don't really notice that with the brass. It's a darker yellow color maybe, but you don't see a a corrosion where it sort of eats away the material, or where there's a layer on top of it. You will also see that there's sort of like a darkish brown mark on it. It does sometimes create this over the brass, especially if it's in heavy weather conditions. But other than that, it is a relatively strong material. And we'll look at some of the applications where it gets used, like in bushes. I've got actually a bush over here, which is, if you look at it and compare it with this brass, you'll see it is a less yellowish color. And the reason for that is that the brass can have different percentages of zinc in it compared to the amount of copper. So depending on what combination you have will give you a different yellowish color in terms of the actual brass. But bushes we'll be looking at also a bit more in detail, but that is sort of the properties that you have with brass. Okay, then we're looking at aluminium. So aluminium has got the advantage that it's light in weight. I've got an aluminium bar over here, and if I've got to pick up a mild steel bar of a similar size, it would be really heavy. I would have to actually pick it up with my whole hand. Over here I'm sort of balancing this with my finger. It's very, very light. Being lightweight has got its advantage, but it's also soft. You can bend aluminium more easily compared to mild steel. And then it's prone not to corrosion. And actually, if you look at this piece of material over here, you'll notice that this piece is cleaned. I just cleaned it so you can actually see the aluminium color over there. And you'll see over here there's like a whitish layer that is on top of the material. So that's what happens with aluminium. It doesn't rust, but it creates a corrosion where it creates like this white powder on top of the surface. And then that white powder prevents further corrosion downwards. You do get aluminium material that do corrode eventually and corrode away, but it is less easier to corrode aluminium compared to, for example, your mild steel. Then we've got stainless steel. So stainless steel is often used in knives, and you will often see that on most knives it might say that it is made from stainless steel. So if you look at this Leatherman, you will see that the stainless steel blades, it is shiny obviously, but it's also very hard, and that's the reason why these blades are made from stainless steel, so that you're able to cut through it without having it to break. You also don't want it to become easily blunt, so the edges, once it's sharpened, would be able to stay sharp after you've cut objects. Obviously, all sharp objects can become blunt, but it won't be as easily becoming blunt. So it's a very hard material. It is heavier, much heavier than, let's say, the copper, brass, aluminium, or mild steel, and it's not supposed to rust. You will find that you might, and I say not supposed to rust because you do find sometimes that knives, for example, which are made from stainless steel, will be able to rust. You leave it out in the rain, leave it outside for a couple of days, and you'll see rust forming on top of it. And it all depends on how much carbon is in the steel. Keep in mind, stainless steel is essentially your normal mild steel. They've just removed the carbon, they've purified the material. So depending on how well it's purified, it's going to identify in terms of how easily it's able to rust or not. And then finally we've got mild steel. So mild steel is a common material used to make things. Over here I've actually cleaned off this piece of metal over here to give you a sort of an idea of what the mild steel looks like. It is relatively hard, sort of a medium material if you have to look in terms of the different materials we've looked at so far. but it's also malleable. So you can machine it, you can easily hit it and bend it and stuff. While with stainless steel, you might not be able to do it as easily. It can rust. So as a matter of fact, if I now turn this around, you'll see on this side how the rust is appearing. And so this rust is what's common to most metal objects like you might have seen before. It's normally like a reddish brown color that appears, so rust is quite common with mild steel. So it's got advantages in terms of it's easy to machine, and you can also heat it up and cool it down quickly, and you can make it to have different properties in terms of strength, and so. But at the end of the day, it's got its place, but it depends on what you're going to be building. Okay, so shaft tubes and I-beams. And so these type of things are we're going to be looking at. We're going to sort of see, can we use them in an appropriate manner? Where would you use them? What are the properties of them? So we're going to be looking at all those type of considerations. Okay, so what I've got over here is, what we're going to be looking at is shafts, flat bars, round bars, square tubing, angle iron, and I-beams. And we're going to sort of see why they're getting used. Okay, so let's start off with the shaft. If you have a look at this round shaft, probably been used for a motor axle, or for, it could even be an axle for a bearing or so. And so it is relatively strong, or it can be relatively strong, obviously depending on what material it's made from. This is obviously made from steel. And so it's able to work well. You might find that you're able to bend it more easily. To demonstrate this again with the copper shaft that I've got over here, I can actually take it and I can bend it quite easily, because it is it doesn't have the different properties that we're going to be looking at that other materials might have. Okay, so shafts are often used, can be quite useful for different applications. But now let's have a look at the flat bar and compare it with the shaft. Okay, so to demonstrate this, before I do that, let me just show you what a flat bar looks like. So in this case, a flat bar has been bent over here into this specific shape. So it is mild steel, this specific flat bar. It is able to bend easily in that direction. But let's demonstrate this with a piece of press stick again. So I've got a piece of press stick that I've now taken and I've flattened it out to be very similar to a flat bar. Okay, now if I had to take this piece of press stick and I had to hold it over here at the end, and I just had to let go this side and let its own weight sort of eventually will pull it down. And I mean, if I look at from the side over there, you can already see that it's sort of arched downwards over there. So it is able to bend very easily in this manner. Okay. The thing is if I had to keep this flat piece of press stick in this orientation and I had to wait for a few minutes, this is not going to really be bending downwards. It will stay in that shape. Okay, you can even test it out by just using your hands. Pulling the ends up and down in this fashion is quite easy. Yet try and sort of bend it now downwards into an arch or upwards into an arch. Well, with a press stick it's possible, but it's much more difficult to do. And the reason being, with these specific flat bars, is that if I want to take this flat bar and I want to arch it upwards, what's going to happen? We're going to have tensile forces acting in the bottom. So it will be acting over there. Yet we're going to have compression forces acting on the top. Okay, so I'm just drawing in the lines over there showing the compression and tensile forces acting on it. So as I'm bending it upwards, the tensile forces will be at the bottom, compression forces will be at the top. And obviously, we can't create or destroy matter, so those compression forces are going to be there, and it's going to try and prevent you from pushing it even more. I can demonstrate it also with this piece of thin plastic that I've got. And I mean, this is a similar type of ABS plastic that you might find your products might come in, like for example food products might come in plastic containers. It's the same type of plastic. So I can bend this plastic quite easily in this fashion. If I keep it in this fashion and I try to bend it, I can put a lot of force onto that and I'm not going to be able to bend it. Okay, so it's the same situation. You've got compression and tensile forces acting on it. So your flat bar's got the advantage that if you have to compare it to a normal round shaft will be able to bend. Your flat bar will be able to bend, but if we had to orientate this in a way that the width of it would be able to be in the direction of the forces, it would be relatively strong and you won't be able to bend it as easily. Okay, something else just to note over here. You will notice if I turn this flat bar around this side, I clean it up over here, essentially it is mild steel, but this specific piece has been galvanized. So it's a zinc layer that has been plated on top of it. And it can be also, you get different ways that you can get the zinc layers on. You can have a cold spray that you spray on, but usually it's like a hot dipping system or electroplating system that happens. So essentially with zinc it was also less prone to corrosion, and so therefore if you have in your mild steel which is prone to corrosion covered up with this zinc layer, it's going to protect it from corroding that easily. And I've got over here also a piece of material that has got it's been galvanized, or the zinc layer has been placed on it more recently, so you'll be able to see it's more shinier compared to this one, which obviously has got a little bit of corrosion on it, where the zinc has formed some oxide layer, not corroded away though, but it's formed an oxide layer, and so it protects your mild steel very well. You can also do it in terms of often it is that you've got some mild steel and you need to have a wire soldered to it, and what's quite useful is you can dip it into copper sulfate, for example, in a solution, and a copper layer will go over it, so that will also protect the mild steel. Or you could even do some electroplating systems and allow it to solder onto the steel via that little copper piece of or that little piece of copper layer that's been electroplated. Okay, so galvanizing is quite useful. Otherwise you would have to take your mild steel and you would have to paint it and make sure that and that's essentially what your vehicles are done in terms of the bodywork, is that they are painted and therefore protected from corrosion. Because remember, corrosion needs water, it needs iron, and you need oxygen. So if the water and oxygen is taken away from the layer, it will prevent corrosion to happen. Okay, so you would often find that vehicles or cars might actually rust, and it is because often the paint might have chipped, might be a stone chip or so, and in that specific place will start rusting. Okay, so now that we've looked at the flat bar and sort of seen the compression and the tensile forces acting on it and why it is possible to bend or not, let's have a look at a round bar. So I've got this round bar over here. This again, it's a steel pipe that's been galvanized, and again we've got a situation that if you look at it, the same scenario is going to happen. If I'm going to try and pull it in an arch going upwards, you're going to find that there's going to be compression on the top, while tensile forces at the bottom. So that compression forces will prevent it from wanting to bend. Yes, you are able to bend pipes, but it is much more difficult compared to a shaft. Similarly, I can show you this with the copper pipe. So I mean, we had to look at the copper shaft. It was easy to bend. I've got a copper pipe over here, and if I add the forces onto it, I can feel it's wanting to bend a little bit, but it's much more difficult. And if you look at this specific copper pipe, which is essentially the same copper pipe we had to look at previously, it is very thin walled. It's not a very thick walled copper pipe, and so even with that little bit of wall that we've got there, it's pretty strong, and you're not able to bend it, at least not as easy as a copper rod. Okay, so keep that in mind with these round bars. It's less material that's being used, but again, we've got a situation. If you want to try and bend it upwards, you're going to have the compression on the top and the tensile forces at the bottom. Okay, then let's have a look at square tubing. So we had a look at this piece of galvanized square tubing already before, and I've got over here actually a square bar. So it's not a tubing. You can see it's a solid piece. And again, same situation would happen with the solid piece. You'll be able to bend that. I mean, it's going to be difficult, but you'll be able to bend it very easily. The solid piece is hard. It's very heavy. It's very thick. But you'll probably be able to bend it more easily compared to square tubing. Square tubing, but again, we've got a situation that we've got now a flat surface over there. We've got a flat surface over there, so that on the top there's going to be compression. At the bottom there's going to be tensile forces. But then again, we've got essentially, if you look at this piece over here, and you look at the piece behind it, it's a flat bar. And we know that with flat bars, it's not easily to bend it in that type of orientation. So that gives your square tubing strength, that it's actually able to be easier to bend, because we've got these flat bars on either side over there. And so this square tubing won't be easy to bend upwards, downwards, into the page, as well as out to the page, depending on which shape you're going to have your arch going. And so square tubing can be quite useful when you've got some structure that's got quite a bit of weight on it. It needs to be strong, and there might be forces acting on it in different directions. This will be quite a useful piece of material to use. Okay, I've also got over here a square, well, it's not exactly square, but it's a rectangular shape tubing. So as you can see, it is longer in the one side compared to the other side. And so again, the same type of scenario can happen, where we can have again those compression and tensile forces acting on it, and we can get a stronger piece of structure going, depending on the application we want to have. Okay, then we're looking at angle iron, because we had to look at angle iron before with this small piece, but here's a little bit of a bigger piece of angle iron. And with angle iron, you've also got again the same situation, that that you've got maybe a flat surface on top that you can put something on, but we've got over here again a flat bar. So it's two flat bars that are 90 degrees to each other. So having this flat bar over here is preventing the bar from bending upwards and downwards. But again, this bar over here will prevent the bending inwards and outwards of the page, depending on how you hold this piece or this specific flat bar. So it is very useful. It's also got strength properties that will prevent it from bending. Very similar to your square tubing, but obviously less material used. Essentially, it's a half a square tubing. Okay, and then finally we got I-beams. Now I-beams, as I've drawn over here an example, they are quite big. They are normally used for roof structures, for building structures. You might see them in big warehouses where the walls are not covered. These I-beams are often used because even though it's got the shape of an eye, when you look at the cross-sectional area of it, the issue is that essentially, if you look at it, it is a few of these square tubings or 90-degree angles that you've got. So you've got a 90-degree angle over there for this piece over there. You've got so for that piece over there, we've got a 90-degree angle over there. For this piece over there, we've got another 90-degree angle that's acting in that orientation. And then we've got again two 90-degree angle irons over here at the bottom, as well as over there to the right. Okay, so therefore we've got the stress properties that are, or at least the compression and tensile properties of this beam. So if we've got some weight acting on top of this beam, this flat bar that is represented over there, okay, so that vertical section, which is of the eye, that is going to essentially prevent it from bending, because essentially we've got a flat bar scenario as this, so it's going to prevent it from bending downwards. Yet at the same time we've got these flat horizontal pieces going on top of it and at the bottom of it, which is going to prevent the arching towards the bottom or the arching towards the top. And so these I-beams are very useful to make structures really strong and to allow, especially for like buildings and even bridges. It gives that extra support, and with the compression and tensile motion of the different sections of the I-beam, you're able to prevent it from actually bending. Again, forces acting on these I-beams need to be really huge to be able to cause it to damage or to want to bend. There can be design flaws, and so there's always these safety aspects that you've got to take into account. But at least it is one of the stronger materials. Probably something you won't necessarily use. It will be more for construction purposes, but it will be, you need to be aware of it should you have to come across it with an application like that. Okay, so now we've looked at the different types of shaft tubes and I-beams, and this is important to keep in mind, because what happens if you have to design something, and I'm just going to be giving a few examples over here. Okay, so what would happen if you've got, for example, a chassis specifically for a motor? So you've got some motor, and it's got some, obviously it might be in a roundish shape, and over there's a shaft coming out of it. Okay, so now you've got to make a chassis for this motor. Firstly, you've got a shaft. Maybe you need to lengthen the shaft. So what would you use? Could you maybe use a solid shaft? Or what about a hollow shaft? Or a tube? You know, so depending on the application, you might want to link up your shafts with a tube. Okay, but then you need to maybe have a bracket over here on this motor, and like I said, connect it to the chassis. So you might need to connect it over there, and you need a base plate over here maybe. Okay, so depending on the application, it's going to be difficult. How would you mount it? Well, if you've got holes at the back of the motor to mount something on it, there might be some bolts that you can mount onto something over there. You might want to use some square tubing over here. So square tubing will allow that this motor won't be able to move at least upwards and downwards, because you've got at least this bar that is keeping it in place. At the same time, it might prevent it from moving inwards into the page or outwards of the page. You could even use square tubing over there. The flat bar over here, you might feel like, oh, a sheet of mild steel might work. But the problem with a sheet of mild steel is that there is a possibility of it warping upwards or downwards. There's bending able to happen. Because essentially, that flat sheet that you've got at the bottom is like this piece of plastic placed in this position. And so you will be able to bend it upwards and downwards. Okay, so maybe for that reason, you need to put some supports over here at the bottom. This could be maybe square tubing. Okay, so if we have to look at it from the side over there, so that could be square tubing. You might even use angle iron if you want to, for that support at the bottom, a few strips of that to prevent it from lifting upwards and downwards. Or otherwise a couple of square tubing in parallel with each other. Okay, so when you see a problem, see where the forces are going to be, how this might be forcing upwards, downwards, into the page or out of the page, and select your material accordingly. What about if you've got something like an electric box? Okay, so you've got some electronics, maybe there's some IC that is connected to, well, on some PCB, printed circuit board, and you need to make a box for this. Well, are you going to make your box out of metal? Probably not, because that's going to cause it to, or that could cause that you could short your electronics. Maybe it would be a good thing to have all your electronics within the side of a plastic box, which won't be conductive. But you might find that also there's not much forces acting on electronics. So your electronic box might need to be, can be made out of plastic. It'll be strong enough, but the structure around it, the chassis that the electronic box is going to be mounted on, that could be a different situation. That might need to be some strong material, because there could be other motors on it and stuff, and therefore you might use your mild steel. But your electronic box will not have to be that strong, because there's no forces acting on that specific electronic box. You do get situations where your electronic box that you might have needs to be a Faraday cage. Okay, so you might have an electronic box like this, and you've got your electronics inside of that, so that might be a little PCB inside over there with your mic controller on it. And to prevent interference from signals coming from outside, you need to shield this off and ground this whole box. So what you could do is you could have a plastic box for the electronics itself, and then place this whole electronic box inside of a metal box. But again, so much work, not much forces acting onto these specific boxes. So you could find that it might be good enough to use your printed circuit board materials, or the PCB materials. If you keep in mind that is a sheet of fiberglass, probably about 1 millimeter thick, and then it's got a very thin layer of copper on top of it, and then that you're able to etch to be able to make your printed circuit boards. So you might be able to take that and place it on into this specific cube shape, and you're able to solder it together, and that will create this Faraday cage around your circuitry. What about in a situation where you might have to build a structure, and let's say it's, for example, a table. So if you've got a table, you're obviously going to need 4 legs. So we're going to have basically 4 legs over here. And again, I'm just drawing it very roughly over here, just to, because initially you will draw your requirements very roughly, and then from there you would work on it and improving on it. So I'm just going to go like this. We can see there's 4 legs needed. We can see that because the 4th leg over there is just protruding out over there. There might be quite a bit of forces acting down over here. It might be, for example, a table for a computer. So there might be forces acting on it, but you need to keep in mind, if you just have a flat sheet over there, will that be strong enough? You might find that typical students might be sitting on the desks, and so there could be a lot of extra forces acting down on it. So maybe there's a need that you need to have underneath this flat sheets some or other angle iron that you can place across in strips that will be in this orientation. So it's obviously angle iron acting like that. And then also you might, so you might have one over there, you might have one over here on the side, as such, and maybe over here on the side. Okay. So you might have your angle iron specifically over there. But then again, if you think about it, this could will prevent the table from bending in this way. But what about it in terms of the table, if it's in this type of formation going into the page, it prevents it from bending that way. So we might also need to have a strip of square tubing or angle iron here on the sides. Maybe over here in the center as well, and over there, just to make it stronger. Keep in mind, you've got to think about safety. If a person should sit on this table and it should break, maybe it should bend very easily and collapse, person could get injured, your computer equipment could be damaged, so that needs to be taken into account. Then we've got the legs of the table over here. What would that be made from? Well, we could use square tubing over there. That will make it strong. It will be also looking good. So you might find that a lot of times the steel tables that you've got, the legs are square tubing. Or you could have round tubing. Maybe it's round tubing would look better. Again, depending on the length of these legs, we need to also take into account, will they be, maybe, especially if it's like round tubing or so, would it have a tendency to wobble a bit? So we might find that we need to have maybe some flat tubing that we weld across over there and create like an X shape on your legs, just to get it a little bit more secure. And it's a beam structure essentially that we with struts and ties, just to keep everything in place. So there might be some of these beams that will act as struts and some of them that will act as ties. So depending on the application that you're going to be doing, have a look at what forces are acting on it. Have a look at whether there's actually a need for the different materials that you need. Sometimes you might find that it is it's not needed. Okay, so for this is obviously an electric box, and this over here is for a table. Okay, so like I say, you might not need to have as much material or as strong material. Like for example with the electric box, there would be no need to make the box out of square tubing and then to cover it with flat sheet of flat material like iron maybe, because essentially the plastic will be strong enough. But when it comes to a table, there might be more forces acting on it. You've got forces acting on from the top. You've got forces acting from maybe from the sides. Maybe somebody comes and kicks the table, and that causes the table needs to be strong. So you need to take that into account. And depending on, as I said, depending on your application, design for it so that there are strengths in the different directions as required. So often it is a shaft that you've got, and that needs to rotate, especially inside some material. And we're going to be just looking at some of the things you need to keep in mind to make sure that the shaft is able to turn very easily. So one of the ways that you can have is to have a bush, like for example this brass bush, and essentially you would have your shaft going into it, and that would allow it to then turn. And so I've got over here an example of a bush. So we've got this block over here that supporting this shaft, but there's not space much space over there. So what's happened is there's one of these bushers have been placed into that shaft over there, and this or inside of this block over here, and this shaft over here is then running inside of this bush. So obviously you need to grease it and oil it. In this specific one, you'll see that there's a little point over here that allows you to have access where you can unscrew this. It's a hole that goes all the way through up to the shaft. You can place your grease in over there, and then you're able to lubricate that shaft by just closing this bolt and turning it every time you want a little bit more grease to go in and to lubricate the system. So that is the reason why you would find that a shaft or a bush such as this one would have a little hole in it, and that will allow for the grease to be able to go through to the shaft and to lubricate the system. But if you have a look at this specific shaft, to turn it is quite difficult. It's not too difficult, but it takes a little bit of force required to turn it. And often it is that little bit of force is critical. You need to make it turn much more easier, and for that reason bearings will be used. Something else just to keep in mind is that sometimes these bushes can also be made out of Teflon. And Teflon's got a property that it is self-lubricating. So if there's not too many harsh forces acting on these bushes, you can have the bushes made out of Teflon, and that would allow that you don't actually need to worry about lubricating it with these grease holes as such, because it would be able to, because of the self-lubricating properties that it's got. A bearing essentially has got little ball bearings, little balls over here where the plastic is, and that allows the inner part to rotate much more easily compared to the outside of this bearing. So essentially I can have a bolt like this or some shaft that I place inside over here, push through onto the bearing, and now if I had to hold this bearing, you're able to turn this quite easily, and you'll actually see that this bolt or shaft that I might have in here will be able to turn very easy and spin very easily compared to the shaft that was in the bush. It wasn't able to spin as easily. And so you can also have something like this spindle. So you might not be able to see the bearing inside of it, but it's able to turn very easily over here because of the bearing over there. If it was a bush, it would have been much more difficult, and there'll be some friction over there involved. And with this specific application where you've got the spindle, you want to minimize the friction over there, and so therefore they would have a bearing inside of here to allow it to move more easily. Printing. 3D printing is a new form of technology in terms of manufacturing, where in the past it used to be that you would take a block of steel and you machine away from it until you get to the desired shape. 3D printing, which is also known as additive manufacturing, applies the layers of the material one on top of each other and builds up the material from scratch. Okay, so whenever I get people coming to me and like, oh, they want to 3D print something, or they're busy with a project and they want to 3D print it, I almost immediately get a bit irritated. And the reason being for this is that often it is that it might be a certain part that I need to have, and might be just a round bar. And that round bar might be something that you can buy in the shops. It will be made already out of, let's say, out of mild steel, and it will be strong and it will be able to do the job. And so even if it means that you've got to buy this shaft and you've got to machine it off a millimeter or so, that process is quite quick to happen. While with 3D printing or additive manufacturing methods, you find that it takes a lot more longer to do. And the reason being is that it's got to build it on a layer on top of another layer. And so something that would be possibly doable to machine a part within a half an hour might take maybe 24 hours to 3D print. So it is very much needed that you need to identify, is it needed to be 3D printed or not? Complex shapes is quite useful for 3D printing. So I've got over here an astronaut that I printed from with a 3D printer. You get different colors and shapes and stuff. So as you can see over there I've got it in a sort of a grayish color type of material. This is more of an ivory type of color, and then this is more like a glass type of finishing, which is it gives you almost that crystal-like effect, obviously not as strong. And then over here I've got a red one, a little red astronaut. So these type of 3D printing techniques are quite useful. Now, so the thing is let's have a look at the different type of printing that you can do. So first you can get is a fused position modeling, which uses a very thin filament, very much like a wire type shape, as you can see over here, and that feeds through a heated extrusion point and then places the layers on top of each other. Okay, so these FDM type of printers that uses these filaments are the cheapest ones available, and you're able to do quite a lot with them, like these little astronaut men that I made, and they all made with the FDM type of printer. So there is quite a lot of uses for it, especially if you want to go and make something as a prototype. You need to identify, is this going to work? Is the shape going to be correct? Maybe you need to do a little bit of modifying or so, and it's a cheap solution to do your prototype and then before you do the final product. The problem with FDM is not as strong, and the other one that you get is a SLS type of printer, which is selective laser sintering. So this is where it uses a powder very much the same as this, and this powder is able to it is in a big container. This is ABS plastic powder, and so what happens is that this powder gets melted with a laser, and the fusion of that laser with the different layers is just a much stronger fusion, therefore you get a much stronger product. Okay, so let's have a look at a part that's been 3D printed, and that specifically it would be for this ring that I've 3D printed now recently. Okay, so this ring was printed with a FDM printer, an NX-A8 printer, and it is able to do a relatively good job. I mean, this ring was printed in this specific position where the extruder was on the top, and it was busy printed in a round circle. I then attempted to print it in a vertical position, so that would be where it would be in this type of position, and it would be building it upwards. And I just started it off over there. As a matter of fact, you'll see I haven't even completed it because it's not the most effective type of way of printing, and I'll show you now soon why. Okay, so printing it, if you look at this diagram over here, you'll notice that I've got the different layers, and depending on the orientation it was printed. So for this specific one, it was printed from the bottom upwards, and therefore you've got your different layers in that type of fashion. The problem comes in that if I apply, if this bottom piece is secure, so that is secure to some ground over there, and you apply some force over there, what's going to cause is it's going to laminate in between those different points. And the lamination, especially with FDM type of printing, is quite common. If you have a look at this astronaut over here, you might be able to see over here the different lines as the print was made going towards the top, and you could probably see a little bit of laminating happening over there as well. So this is quite an important thing, because that means it's quite weak over there. So applying a force over here is going to cause material to laminate over there, and it would probably then snap across over there. It will shear because of the weak laminations. If you had to print it in an orientation where this was probably printed in this fashion, so consider this to be the bottom, and then start printing it from the top, and you've got your different layers like this, it would give you a stronger type of material. Again, if we had to fasten this and secure it to the ground and apply some force over there, it's not going to shear as easily. And you can think about it as being, essentially, we're going to, if we apply force over there, there's going to be some tensile forces acting over there, there's going to be some compression forces acting over there, and it's going to be less likely to actually shear and or even bend. And so this is an important factor to keep in mind. So if you look at these specific parts that I've printed over here, with this one that I just started at the bottom, I could, so it was positioned in this position and was printing it upwards towards the camera. Okay, so that is very much the same fashion as with this type of diagram. It was over there at the bottom, and it starts building the layers on top of each other. Now this, I mean, I can already, just with this little piece, I can apply force to it, and you can see it snapping already at those different layers where it's made. It just shears. So if you compare it with a piece of this one, which was now printed in very much similar orientation as that, I can, so in other words, it was printed from the top with a circular fashion, with a heating element and extrusion of the wire. With this specific one, I can pull on it, and yes, you might find it's going to break, like you can see over here, it's breaking on a corner maybe, there's a weak point, but the amount of force I've got to do it is a lot more. And that is because there is not, I mean, you've got a tension in those orientations. So to break it is much more difficult. As a matter of fact, if I try and destroy it over here, yes, I'm going to break it because it's a very weak piece of plastic, and it's probably at those joints or at those corners that you'll find it breaking. So the orientation is very important. 3D printing has got its place. 3D printing is a useful technique to use, but my advice is, if it is, you need to look at the item that you're going to be developing. If it is something that is of complex shape, like for example the little man that we had to look at, then by all means, to go in 3D printers is going to be much more easier and quicker than taking a block of plastic and machining it out to be in a shape. If it is going to be something that's going to be like a plastic cylinder, for example with this pen, you might find that it's going to be easier just to machine it. With a plastic rod, draw a hole in the center of it and machine it to the specific thickness that you want it. Also keep in mind that when you 3D print, and we're looking specifically now at this tube of this pen that we looked at, you need to keep in mind that there needs to be often supporting material. So if you're wanting to print a tube, as in this fashion, the printing of the bottom layers are going to be fine, and then maybe the printing of the side layers are going to be fine. But what's going to happen when it comes to printing the material at the top? And often you need to have actually supporting material over here so that the printing is possible to happen on the top Otherwise the material will just fall down into this cavity. And then the supporting material needs to actually be removed. So that's often just removed by a screwdriver or a drill bit or so, but it might be needed to be done. So again, the amount of time it's going to take to machine a tube out of plastic might take you 15 minutes or so, while if you have to go and 3D print it, it might take you about a few hours. So it's very important to keep that in mind. Also very important is the orientation that you're going to 3D print it, because you've got to look at what forces there's going to be. If there's going to be a force applied to the material, it is best to make sure that the orientation or the way that it's printed is at 90 degrees to the force. Okay, so in other words, if you have to look at it, it's in the same direction of the force, depending on how you look at it. So to put into this perspective, if you had to 3D print it from the top, okay, that's going to be the head will be from the top, the force will be from the side, so it will be weaker. So at 90 degrees to that, it would be weak. Yet if it's printed in this orientation, and the head is here, and that's the top. So in other words, if I turn it around like that, and suppose you're printing it from the top as such, you're going to find that if you have a force applied over there, which is going to be in the same axes as the head, then it's going to be stronger. Okay, but again, the layers are going to be at 90 degrees to the force. So that's going to be the strongest point you're going to have. While if the force is in the same direction as the layers, you're going to have a very weak type of material. So it's very important to look at what you're going to use the part for, how it's going to be printed. Sometimes if there's forces required to be acting on it, 3D printing might not be the best way to manufacture the part. Maybe machining it from a piece of material would be best. Yet with SLS or laser sintering type of printing methods, it is a stronger bond. It's a stronger bond between the different layers, and therefore it could possibly have larger forces acting on it. So these are just things you need to keep in mind whenever you do 3D printing, so that it is the best option for this part that you're going to be using. It's also going to be the best option in terms of what forces are going to be acting on it. And then you also need to look in terms of time. Time is money, and time is what's going to determine, whether it's worthwhile to manufacture a product in that way or not.